Now we talk about the stop bit, right? To signal the end of the data packet, the sending UART drives the data transmission line from low to high voltage for at least 2-bit duration. So when the data transmission is complete, right? When this part of the transmission has been completed, to complete this data packet, right, this 1 or 2 stop bits are sent. Right, and what is a stop bit? The data transmission line, right, is pulled up from a low voltage to a high voltage for at least 2-bit positions or 2 TBs, right? So if the stop bit is not there, its presence will result in a framing error, right? Why is that? The start of the packet was started, but the end was not indicated using the stop bit. So the packet is not complete, or the data frame is not complete, so it results in a framing error. So let's look at this. This is the data bus, this is the transmission UART, this is the receiving UART which receives serially, right? This is the idea. So the transmitting UART transmits serially to the receiving UART, and the receiving UART, of course, converts the received serial data into the parallel data for the receiver. So this is the idea. Now finally we turn to the errors in serial communication. One of the errors is the framing error that in fact we have already discussed, right? If the start bit has been received and the data bits have been received, but the stop bit has not been received, it means the data frame was not complete, and this results basically in a framing error. The next error is the parity error, and afterwards we would have the overrun error, right? So what are the advantages of UART? In asynchronous mode, of course, it uses only 2 wires, so no clock signal is necessary, so no complications of the clock, and it has got parity bit to allow for error checking. The structure of the data packet can be changed as long as both sides are set up for it, right? You can have a data packet for 5 bits, you can have a data bit for 6 bits and 7 bits and 8 bits, up to 9 bits you can have, right? And it's a well documented and widely used method. Now what are the disadvantages of UART? The size of the data frame is fixed, limited to a maximum of 9 bits. You can't have more than 9 bits of data, right? It doesn't support multiple slave or multiple master systems. So that is the idea. But RS485 supports multiple devices, right? More than 2 devices per channel of UART communication. And the baud rates of each UART must be within 10% of each other. If the difference is greater than 10%, there would be errors in transmission. Now we turn over to the analog signals. An analog signal is a continuously varying value, right? This is an analog signal, just like a sine wave. AC voltage in your homes are transmitted in analog signals of sine waves of 50 Hz. And the resolution is infinite in both time and magnitude. So in this scale also there can be infinite values, so the waveform is very smooth. And on this direction of the time axis we have infinite values, so the waveform is exactly very smooth, right? A 9-volt battery is an example of an analog device in which its output voltage is not precisely 9 volt, it changes over time, right? So if you apply load to a 9-volt battery, the voltage is going to be changing, and it can take any real numbered value, right? Similarly, the amount of current drawn from a battery is not limited to a finite set of possible values. So how are analog signals distinguishable from digital signals? Because digital signals always take only values with discrete values, right, from a finite set of possibilities. So for example, and your digital signal may have a discrete value of 0 volt or 5 volts. 0 volt meaning logic 0 and 5 volt meaning logic 1. Let's now talk about digital signals and pulse width modulation, which is also termed as PWM. Right? So what is PWM? By controlling an analog circuit digitally, system cost and power consumption can be drastically reduced. So PWM is the method of controlling an analog circuits via a digital method. What's more, many microcontrollers and DSPs already include on-chip PWM controllers, which are called PWM modules, which making implementation easy. Right? So already included are the accessories of PWM controllers, which you can just program and configure for a particular mode of operation of pulse width modulation of PWM. So in a nutshell, we can say that PWM is a method of converting from digital to analog. So this is one way of putting PWM together. So what is pulse width modulation? PWM is a way of digitally encoding analog signal levels. So we want to create analog signal levels, but we code them digitally using PWM. And how do we do that? We use high resolution counters, right? Which have a high resolution, so that we get more accuracy. So what do we do by those high resolution counters? The duty cycle of the square wave is modulated to encode a specific analog signal level, right? So for example, if we have 12 volts, right, and we want to encode, let's say if we have 12 volts analog and we want to create a 6 volt analog signal, what do? We apply a 50% duty cycle PWM signal, and that 50% duty cycle PWM signal, what it does, it turns 12 volts on half of the time and it turns 12 volts off half of the time. So the effective voltage created is half of this 12 volt, which is 6 volts. So the PWM signal is still digital, because at any given instant time the full DC supply is either fully turned on or fully turned off, like I said before in this example. So what is the condition? That this bandwidth should be sufficient. It should be a high bandwidth signal. If PWM is a high bandwidth or a high frequency signal, the analog voltage can be created very efficiently and very accurately. But if the frequency of the PWM signal is low, there would be a lot of distortion, and the created voltage, analog voltage, won't be very smooth. That is the idea. So let's look at the PWM example, right? PWM, this is the PWM, an analog signal created by a PWM wave. It looks something like this, right? So this is less smooth, this is more smooth, right? So this is the better analog voltage, this is the less nice analog voltage created by PWM. So the figure shows PWM output at a 10% duty cycles, right? So it is 10% duty cycle, right, for the time t. Of course, if we have the signal is on for 10% of the time and it is off for 90% of the time. So this is one time period of the pulse width waveform wave, right? So if we have time t, which is from here to here, the frequency would be 1 over t, and we call it PRF, or pulse repetitive frequency. Okay. So for PRF, right, if 5 kilohertz is not good, 200 kilohertz is much better. The higher this PRF, the better and smoother our created analog signal would be, right? So for example, this output can be termed as the output for 200 kilohertz, and this output can be termed as an output for 5 kilohertz. So this is called basically THD, or total harmonic distortion. The quality of the analog signal created by PWM is measured by THD, or total harmonic distortion. Less total harmonic distortion, better signal. So this signal has got low THD as compared to this signal. So for another PWM example, this figure shows PWM outputs at 50% and 90% duty cycles. Why? Because this is basically the time period. The waveform is on 50% of the time and is off for 50% of the time. So 50% duty cycle, what's the duty cycle over here? It's on for 90% of the time, it's off for 10% of the time. So duty cycle is 90%. So how do we interpret that? These three PWM outputs encode three different analog signal values at 10%, 50% and 90% of the full strength. Right, so if the supply voltage is 9 volt and duty cycle is 10%, so 10 over 100 into 9, which is basically 0.1 volts, 0.9 volts, sorry. Similar is the duty cycle at this, which is 50%, right? So it would be half of the voltage, or 4.5 volts. At 90% it would be about 8.1 volts, so it's basically 8, right? 8.1 volts. And if the duty cycle is 100, the waveform is never off, so we get the maximum with the full voltage, right? So this is the interpretation. So we can have another example of a circuit that can be driven using PWM, right? And what does it do? It powers an incandescent light bulb with a 9 volt battery. Close the switch connected battery lamp for 50 milliseconds. The bulb would receive 9 volts during that interval. Open the switch for the next 50 milliseconds, the bulb would receive 0 volts, right? So this is how the thing is working. This is a simple PWM operation, right? So if we repeat this cycle 10 times a second, the bulb will be lit as though it were connected to a 4.5 volt battery. Why? Because the duty cycle is 50%. Why it is 50%? We are switching on for 50 milliseconds and switching off for 50 milliseconds, right? So the duty cycle is 50%. And if we do it 10 times a second, it would be this. So we say that the duty cycle is 50% and the modulating frequency is 10 hertz. Why is it 10 hertz? Because we are doing this operation 10 times a second. Now, to have a very beautiful effect of this dimmer, right, we should increase the frequency of the modulating signal, or modulating frequency, the frequency of the pulse width modulation signal, right? The same is true for applications of PWM. So common modulating frequency range from 1 kHz to 200 kHz. So your SMPSs or switching mode power supplies use these PWM signals, and they use it in the range of about 25 kHz for the older models to about 100 plus kHz for the newer switching mode power supplies. We know what is the advantage of increasing the frequency, right? Increasing the frequency have got many great advantages, right? Inductance is driven by frequency 2 pi f L, isn't it? So that is the idea. So when we talk from the terms of capacitors, right, why basically increasing the frequency is good? We want to investigate why we are increasing the frequency. What is the main benefit of increasing the frequency, right? So for that we look at these two formulas. This is the capacitive reactance Xc equals 1/2 pi Fc, a very basic formula, and we can see clearly that if we want to have a particular value of Xc, we are increasing F, right? So if we are increasing F, we must decrease C by a corresponding amount to get the same value of Xc. So when we decrease the capacitance C, we are decreasing the size of the capacitors that are in our power supplies or power equipment. So we are having a reduction in weight of the device. Similarly, XL equals XL is equal to 2 pi FL. This is the inductive reactance XL, right? So for a particular value of inductive reactance, when we increase frequency F from 1 kHz, for example, to 200 kHz, we must decrease L by the same corresponding amount so that XL remains the same. So in this example also, since F is increasing, L decreases, size of the inductance decreases to have the same value of XL. So this also reduces in the results in the reduction in the size and weight of the device. So that's the basic idea. So most loads, inductive and capacitive, require a much higher modulating frequency than 10 Hz, right? So imagine that our lamp was switched on for 5 seconds and off for 5 seconds, and once the duty cycle would still be 50%, but the lamp would appear brightly lit for the first 5 seconds and off for the next. So the idea is we must do this duty cycle at a very high frequency so that we have a very good result. This is again another application or another discussion about the pulse width modulator, which is now being treated as a peripheral. So pulse width modulator's main function is to convert digital to analog. So modern microcontrollers and modern embedded systems don't have D2A converters. Instead, they have multiple PWM modules because they are easier to build and they are much compact as compared to the digital to analog converters. So this again the duty cycle that has been provided and the different results that are there. So they are simpler than DC to DC converter or digital to analog converters. So what are the common applications? DC motor speed, dimmer lights. And another use, we can encode commands, right, by using a PWM signal, and can decode at the receiver end, right. So for example, we might be having sequences of pulse width modulation for a certain level for logic 1 and a certain level for logic 0, and we might do that, right. So this is the idea.